Hello, so this week's lab is lab 4 and it covers oscillations. In this lab I analyzed the motion of a spring mass system undergoing two-dimensional oscillation. Mass not only oscillates vertically due to the spring, but it also swings horizontally. The goal was to create or compare experimental data from the video analysis with the computational model based on physical principles. And some useful equations include Newton's second law and the energy principle. And here's the code I used. I basically changed out the mass and the position, and then changed the spring constant and then the relaxed length of the spring. And then here's some more code. It's just updated lines. And then here's like the bulk of it, which you can kind of see like this, the position update and then velocity update and then just everything else filled in. So here is the model versus experiment. So when comparing the model to the experimental data, they both show oscillating motion forming an oval shape, but the problem is that they don't overlap quite correctly. And a strong reason for this error is most likely due to tracking issues, and then the fact that the model is negating air resistance, and then the spring is going to be assumed as an ideal spring. Despite that, though, the differences are really off, so I think a lot of the error did come in tracking, and it wasn't quite done correctly. So here's the graph showing the energy, like the change in energy over time. It basically shows the changes in kinetic energy, gravitational potential, the spring potential energy, and then the overall change in energy. So these energies continuously exchange with each other during the motion, and then the question is like, is this energy principle satisfied? And the answer is yes, because the change in energy stays around 0. There's like small deviations, but these are due to like numerical approximation and then measurement noise from the tracker video. But I think it's interesting, like although there's a lot of error in the video analysis and then in the like previous slide we saw, it still shows a satisfied energy principle because there's still like no external forces acting on this system. And then here is the period comparison. So the oscillation period was determined by measuring the time between successive peaks in both the x position and the y position graphs. And then I basically wrote like, you can take multiple peaks and then take the average to get like a better period. And then from the x directional data, the period was approximately t equals 1.65 seconds, and then for the y direction, it was approximately 1.52. And these values are similar, but not exactly the same. And it's because the system undergoes two-dimensional motion, where the horizontal swinging and vertical spring oscillations are like coupled, I guess. And basically, unlike like one-dimensional motion, like if it's just in the y direction or just in the x direction, the motion here is involving interacting components, so one single period does not describe the system, which is why we have to take these averages. And then these will ultimately affect the spring constant because the periods are used in that formula. So I thought that was important to note. And then that's basically it. Overall, the model successfully captures the general behavior of the spring mass system, even though there are lots of errors. While there are differences between the model and experimental data, these are explained by the limitations of the model and measurement errors, kind of like I said before. And then this lab demonstrates how fundamental principles of physics can be used to model complex motion, while also highlighting the challenges of comparing like idealized models with actual real-world data. So the discrepancies show also that like a simple vertical spring model does not fully capture the dynamics of a full-on two-dimensional spring system, which I also thought was important to note. And that's basically it. Thank you for listening and have a great day.